Again, welcome everyone, and thank you for joining us on today's webinar, Surge Relief Solutions for Liquid Pipelines. Before we begin today, I'm going to take a brief moment to orient everybody to your webinar environment. On your screen, you're going to see a presentation window on the left side, a Q&A chat window in the upper right-hand corner, and a resource box with related content where you can view and download any relevant content that you'd like during the event. You can resize, move, or minimize any of these windows per your viewing preferences. And you'll also notice at the bottom of your display that you have a row of icons that give you some added capabilities, such as you can share this webinar via social media channels, or you can even contact one of our flow experts and even schedule a visit. Throughout our presentation, we encourage you to interact with our speaker by typing in any questions or comments you have using that chat panel, and we will be answering all of the questions at the end of the webinar. We are also recording today's webinar, and we will make a link to this recording available to you roughly 24 hours post-event via email. So sometime tomorrow we'll be sending out, again, a link to this recording where you can share it or review it again. And on today's webinar, we are lucky enough to have joining us Dave Seiler. Dave has actually been with Emerson for over 37 years and has held a variety of different roles, including 15 years as an expatriate in the Middle East and Europe. He is an active committee member of the American Petroleum Institute and has had papers published in hydrocarbon processing, world pipeline, and is an instructor at the International School of Hydrocarbon Measurement, the Canadian School of Measurement, and also has presented at the North Sea Flow Measurement Workshop, as well as at various CC conferences around the world. Welcome, Dave.
Thanks, Allison. Hi, everybody. I'm Dave Seiler with Emerson Flow Systems and Solutions, and I'd like to thank you for joining us for our Surge Relief webinar today. So, our agenda, we're going to define what is surge and how does it affect our customers, what are some of the customer challenges being faced today, what solution does Emerson bring to the table and how can we help, what are some of the applications that we see. We've got a reference list, some additional resources, and time permitting, we will open the floor for questions. So, what is surge pressure? Well, I think we've all experienced it. If you ever open or close a tap in your house and the pipe shake a little bit, that's called water hammer. And surge pressure is also called water hammer, and it's defined as a sudden increase in pressure due to an instantaneous conversion of momentum to pressure. That's exactly what's happening. We've got a flowing liquid, and we stop it quickly, and we get that water hammer effect. So it shakes the pipe a little bit in our household, but it can do some severe damage on large hydrocarbon pipelines. And these surge pressures can significantly exceed the maximum allowable operating pressure, which is known as the MAOP, plus any additional overpressure allowance, which is typically 10% above that. Now, the graph on this chart here is actually showing an orange line and a blue line. We have a typical pipeline pressure with a pump station coming in. We're coming in at about just over 600 psi, and the dashed line is our set point. That's the pressure that ideally we do not want to exceed. And what's happening on this graph, this is actually a pressure signal taken from the downstream side of a pump. What's actually happening here is that pump trips. We've had a power failure or something has happened, and that pump is literally stopped. And you'll notice that the pressure actually decreases dramatically on the downstream side of that pump. That's because while the pump is stopped, the liquid continues to flow. We get almost a bit of a vacuum on the downstream side of the pump. That causes the decrease in pressure. But at some point, that liquid is going to reverse and start coming back towards the pump, and that's where we have the problem coming. And that orange line peaks up close to 1,000 psi without any type of surge relief, well above our maximum limit. And then you'll notice that the pressure decreases and it begins to cycle at that point, kind of like a sinusoidal sine wave as the pressure wave propagates and goes back and forth, dissipating along the way. Well, we've got a couple peaks there that are well above our set point, and this is typically what can happen if we do not have appropriate surge relief. And what the blue line is showing us is what could possibly happen if we had selected a proper surge relief system. That's going to keep us at or below that set point. So that's what we're trying to do, is avoid those dangerous pressures that exceed our safety margin. So why surges occur? Well, we just had one example there. It's the starting or stopping, in this case, the stopping of a pump. Surge pressures can also be caused by the closing of an automatic emergency shutdown device, or an ESD, rapid closure or opening of a manual or power-operated valve, the slamming shut of a non-return valve, a check valve. And it's important to note that pressure waves travel both upstream and downstream from the point of origin. Now, a very rough rule of thumb that's been used in the past to approximate the estimate of that maximum surge pressure is to have a 0.8 multiplied by the weight of the liquid per cubic foot in pounds, multiply that by the velocity change in foot per second. And we'll see here that in this formula, assuming that the product does not change, the variable that we have is the velocity change. So again, that's a very rough rule of thumb. Another one that is sometimes used, that we can say that we can expect about a 50 psi change in pressure with a velocity of every 10 foot per second. So there's a couple rough rules of thumb which have been used in the past, but thankfully technology has gotten to the point where we can do a lot of this through pipeline modeling techniques that we'll talk about in just a few minutes. An interesting note here from the Pipeline Gas and Journal that some pipelines are in transient operations over 60% of the time, which is a very high percentage. Addressing pipeline issues, one of the major issues that we have on pipelines is line blockage. It's a very serious pipeline problem, and every effort is made by the designers and the operators through valve interlocking and procedures to operate without line blockage. We don't want to have any blockage in that line. That could be an ESD, it could be a pump failure. The line blockage can result in a combination of surge pressure and packing pressure. Now, packing pressure we have not discussed yet, but if we think about a pipeline, which is basically a very long column of liquid with the same flow rate all the way through there, I may stop one end of that pipeline, but the other end of the pipeline, that fluid will continue under its own momentum and inertia. It will continue to flow, and it will pack into that closed section and gradually increasing the pressure as it does so. So here we're dealing with, in line blockage on a long pipeline, we've got not only the surge pressure, and we also have the packing pressure. Surge pressure is created during the last 20% of valve closure, and it may be as high as 170 pounds per square inch per second. We're dealing with some enormous energies here that we've got to do something to contain or mitigate. Total surge pressures can be as much as 30 times the velocity in feet per second flowing through that pipeline. The amount of packing that occurs, that's going to vary with the line diameter, the wall thickness, the length of the pipe. And in most pipelines, the real problem is that line pack. So large diameter, high flow pipelines have to be designed for surge protection as well as line packing. So this is just a very basic rough out of a surge relief system. We've got our pipeline down at the bottom, a couple of pipe stations. These may be a mile apart. These may be hundreds of miles apart. But if we can imagine an emergency shutdown device downstream from the pump on the right, and we have an emergency at that station, we have no choice but to shut down that pipeline and close that valve. We're going to have line packing and surge occurring, building up on that pump. And without some way to mitigate, to remove that excess energy from the pipeline, bad things can happen, such as pipe rupturing, flange separation, etc. So what we're doing here is coming off the top of the pipeline, we've got a branch line coming off with a surge relief valve, which is in a normally closed position, and that's feeding into a dedicated surge tank. So that valve is sitting there in the closed position, monitoring the upstream pressure, upstream from the valve, and as the emergency shutdown device closes and the line pack occurs, as that pressure begins to build up, it will exceed the set point of the valve will open, we will remove the excess energy from the pipeline into our storage tank. Once the surge abates and the pressures return below set point, the valve will close, reseat, and we'll be ready for the next incident. So our customers have several operational challenges and often ask the questions, can I manage my surges with reliable, effective solutions? With the goal, we want to ensure pipeline integrity and environmental protection. We want to meet our regulatory requirements, and we want to maximize our capacity and decrease costs. Conversely, there's negative impacts of not managing surge, and these can run from shutdowns and uninterrupted delivery We can have damage to equipment, people, and environment, and not only to mention the cleanup costs and the fines and the public image. We have some time-consuming reports. I'm told by several pipeline operators when an incident does occur, there's a large stack of paperwork that's got to be filled out. Everyone wants to avoid that. We have compliance activities for these pressure excursions. These can delay projects. And if we don't maximize our capacity and decrease cost, then obviously we're operating at a decreased pressure, and a decreased pressure means less throughput, reduced pipeline versatility, and often results in increased maintenance. Ensure pipeline integrity and environmental protection. If we can give a wide range of surge relief valves and complete systems, that will improve our HSE performance associated with injuries and environment. We can avoid fatigue failure and equipment damage and get some better insight into the surge system and improve its life cycle sustainability and reliability. That we can achieve with a properly designed system with the proper diagnostics to go along with it. And the benefits to the user are equipment and pipe protection. We avoid those costs and those nasty fines. We maintain our brand integrity. We ensure delivery. We reduce our maintenance. And we keep the business going. We avoid that business disruption. We want to maximize our capacity and decrease ownership costs. Well, we can help doing that by supplying high-quality turnkey solutions and systems optimization for surge relief. We want to ensure operational readiness. The closer we can operate to that maximum allowable operating pressure, that maximizes our throughput through the pipeline. We want to increase our versatility and avoid fluid losses. High-capacity valves help by reducing system size and weight. We want to extend the life cycle of equipment, and we want to make these things easy to install and maintain. So the benefits are equipment, ensure delivery, unplanned maintenance, and avoid, again, those costs and fines that might come with them. Very important that we meet our design codes and regulatory requirements. The Emerson Flow Systems and Solution Group, our group, we've supplied systems all around the world, and we're very experienced and familiar with requirements and regulation in various world areas. Here in the U.S., and in many parts of the world, in fact, ASME B31.4 is a common standard that's being used. Requirements of 49 CFR 195 for protective equipment are very often used by not only pipeline operators in the United States, but all throughout the world. And we want to increase project feasibility and acceptance by getting these projects cleared faster. So the benefits, obviously, no line interruption. We want to avoid the reports and the compliance activities. And we want to get our projects, when we can get them, completed as quickly as possible. This is just some of the standards that we've dealt with in the past. B31.4 and the Department of Transportation, Section 49 we're familiar with. In China, we have the GB 50253. And we've also had to comply with the regulations in India. So again, we're very familiar with what needs to be done. And while the verbiage might be slightly different from one part of the world to the other, the goal is the same: to do everything possible to mitigate these surges and prevent damage to equipment and personnel. So we're finding really all around the world that surge attention is receiving more attention than it ever has before. And part of that is simply due to the fact that we've got increased flow through existing pipelines. As difficult as it is to get new pipelines built today, we've got an increase in demand, therefore we've got to get more capacity through existing pipelines. So we're increasing rates, we're adding drag-reducing agents, we're doing everything we can to get more flow through existing pipelines and putting additional stresses on there that weren't there when some of these pipelines were put in service 20 or 30 years ago. More financial risk than ever. Nobody wants to have a spill, the costs and the cleanup that goes with it. I'll say no more about that. On the same hand, there's also new construction going on in many parts of the world. There's new pipelines happening in emerging markets. And another thing that we're seeing is that there's improved pipeline model analysis techniques are being used, computer modeling. This didn't exist 30 years ago. And some of the pipelines are finding some of the assumptions that were made many, many years ago, because they didn't have the tools available that they have today, some of the assumptions made and some of the potential surges that were calculated were found to be somewhat inadequate. You take that into account, plus the fact that we're also increasing flow through the older pipelines, and we're seeing many operators on mature pipelines actually enhancing and adding to existing surge relief systems to account for the potential for further surges or additional surges that weren't there when the pipelines were initially installed. So we talked about line pack, we talked about water hammer, many potential sources of surge to consider in the pipeline design. ESDs, pump starts and stops, valves opening and closing. And we really have to be careful that we don't just limit this to pipelines. This really is potentially an issue anywhere where we have flowing of liquids with starting and stopping. This can be in bulk loading terminals, this can be in marine operations, this can be in the production environment, anywhere, airports, anywhere where we've got flow, liquid flow with starting and stopping, we do have the potential for surge. We have to be cognizant of it and do our due diligence. So, pipeline engineer has quite a task in front of him in his design considerations, and hopefully it'll start with complete computer modeling of the pipeline profile during initial stages, not only initial stages, but as I said earlier, even on mature pipelines, many of our users are doing the computer modeling. They're doing a lot of the simulations, what I call the what-if scenarios, and laying out their whole pipeline and running through the various scenarios to determine what are the potential surge pressures that they could be dealing with and what do they have to do to mitigate those or eliminate those or at least minimize them as much as possible. Well, one thing they can do, we can simply design pressure to withstand maximum surge pressure. That might mean building ANSI 900 pipelines all across the world. Well, that would certainly be one solution, but it's not very financially viable. It doesn't make a lot of sense. It's a very expensive operation to build pipelines able to withstand every possible scenario. Stage pump shutdown sequence. Oftentimes, and this is where the computer modeling can help you, we find that if we change our sequence or change some timing in there, that can help to minimize some of the surge pressures. May not eliminate them, but every little bit that we can do to help minimize is certainly a step in the right direction. Staged emergency shutdown of motor-operated valve closure times. If we can extend valve closure times in the event of an emergency, that will also help. But we've got to balance that against the purpose of an emergency shutdown device, which is to shut down as quickly and as safely as possible. So those two have to be balanced. Linking ship-to-shore emergency shutdown devices when we're loading and offloading tankers. Often, if we're doing some type of marine operation, it's critical that the vessel and the tank, the onshore tanks, are in proper communication and they choreograph their activities to minimize surge as much as possible. And then finally, once we do everything that we can to minimize, we may reach a point where we say we've done everything we can, here's our worst case scenario, we've got to have some type of surge relief device. And that's where the selection of that device and that system becomes very critical. Within the Emerson family, Energy Systems International offers an outstanding suite of software that will help with this endeavor. Pipeline Studio is one of the suites they have. And Pipeline Studio, what Pipeline Studio does, it allows complete pipeline modeling to simulate various surge conditions. We can do both steady state and transient simulations. We can change products. We can change flow rates. We can literally lay out the entire pipeline and then do, as I said, what are all the what-if scenarios and see what we can do to help minimize damaging surge pressures. So Energy Systems International, which is part of the Remote Automation Solutions business unit of Emerson, has been a great asset to us and a big help to our customers. This is just a snapshot of one of the screens that are available. There's, on the left-hand side, we actually see a section of the pipeline laid out with all the various components, valves, pumps, motors, etc. And on the right, we're showing a flow versus pressure profile curve. So this literally allows us to put out the entire pipeline, put in our sizes, flow rates, pressures, do various simulations to determine what types of energies are we dealing with and what's the best way to control and mitigate damaging surge pressures. Here's another snapshot of the transient simulation. Again, on the lower left, we've got a flow versus pressure curve. On the red line in the center of the screen is actually showing the pipeline with a pump, some valves, and we're looking at some flow rates. Again, literally just laying out the pipeline. And at the top, we can vary things such as valve closure. We can change our control system. This will take into account pumps spin up and spin down. We can change fluid properties, change flow rates. It literally allows us to place the entire pipeline on a computer screen and take a look and do all of those scenarios to help determine what is exactly happening in our pipeline. So let's look at some of the commonly used surge relief devices that we've seen. These include safety relief valves, both direct acting and a rupture pin device. There are accumulators that are often used. We have rupture discs, and finally we have modulating relief valves. These are just some of the things that are very commonly used throughout our industry. And we'll start with the direct acting spring-loaded relief valve. Very commonly used throughout the industry. We've got direct acting relief valves. We have the rupture pin type valve. We have accumulators, rupture discs, and then finally modulating relief valves. But before we get into that, I'd like to ask the audience just a quick poll question here. What type of surge relief valve device have you used or specified in the past? It would take just a few seconds to give us some insight. We can have a better understanding. All right, got some answers coming in. We've got quite a few folks are using the direct acting valve, rupture disc, surge suppressor, pilot, or nitrogen loaded relief valve. That's very interesting. Okay. Thank you for that. All right, let's move on. Talk a little bit about each one of these devices. The direct-acting spring-loaded relief valve is just what it says it is. It's a valve that is in the normally closed position and simply uses a spring to keep the valve in the closed position. Spring force is the only force keeping that valve closed. The inlet of this valve is on the bottom nozzle, and it's exerting pressure against the bottom side of the seat disc. And as long as the pressure at the inlet of the nozzle is less than the force of the spring, that valve will be in the closed position. So these are completely self-contained. They don't require any electrical power, any pneumatics, or anything else. They simply mount. You think, fit it, and forget. But they're not without some issues. Because it is a direct spring-acting virus, and the only thing keeping that valve is the spring, there's a phenomenon that occurs with these valves, and that is that the force of the spring changes as the valve is opening. If we can imagine a valve sitting there with a set point of 200 psi when the valve is closed, when we hit this thing with a surge pressure at the bottom of that nozzle of 230 psi or some number larger than 200 and we lift the seat off the disc, we're compressing the spring. As we compress the spring, we're also increasing the spring force. So what winds up happening here is the valve opens, the spring force increases, the valve slams shut, and it sits there opening and closing. That's called valve chatter. And that can be a nuisance. That can actually set up some reverse surges. We're trying to take the surge off the pipeline, and here we are with this guy sending it back into the pipeline, so we've got to be careful of that. So, again, it's completely self-contained, but there is the issue of valve chatter, and we have to be careful also of the relief capacities and the flow rates that are possible through these things, unless we put several of them in parallel, which increases their cost. Another type of device commonly used is what's called a rupture pin valve. Now this is an interesting valve. This is a plug valve, and at the top left, we're showing the valve in the closed position. I've got a plug that's seated, tightly closed. I have an inlet force on the bottom in orange, and what's keeping this valve in the closed position is a rupture pin external to the main valve. This is a valve that is on the outside of the valve. It's a rod, and that rod is designed to bend or buckle at a precise force. So the rod is keeping the valve in the closed position. If I have a surge come into the valve from the bottom, once the surge pressure exceeds the strength of that rod will buckle or bend, allowing the plug to come off the seat, and that valve will open, exiting to the right of the valve into our dedicated surge relief tank. These valves operate quite quickly. They're very fast to respond, but they do not reseat. They will not close after the surge pressure abates. So once this guy opens, it stays open. Now, if this valve is out in a remote area going to a dedicated surge relief tank, what that means is we better get an operator out there very quickly to find another valve that is in series with this valve and close it before that tank overfills. At that point, we can isolate this rupture pin valve. We can force the plug back down onto the seat, and then we have to replace the pin. So while it's not a one-time use, each rod is a one-time use and has to be replaced after every incident. So you have to be careful with this, especially using this in a remote area. It is a non-modulating type valve. Surge accumulators. Surge accumulator is very similar to a shock absorber. In this little sketch here, we're actually showing 3 different surge accumulators. Those are items 6, item 9, and item 10. Slightly different in design, but they all operate on the same principle, which is a pressure vessel with a gas-filled bladder on the inside. Think of it as a balloon filled with air. As we flow through our pipeline, and these are very effective on smaller line sizes and relatively short distances, I've got a pump on the left-hand side of the screen, number 2, and I've got a valve on the far right-hand side, number 11. If I'm flowing along and suddenly close valve 11 quickly, I'm going to have that water hammer effect that we talked about in our house. Well, what will happen here is that pressure will enter into each one of these accumulators and collapse the bladder, and it will actually absorb some of the liquid and therefore some of the energy. Now, these have the advantage of not needing a line going to a separate or dedicated tank because we're really not removing any liquid from the line. We're simply allowing it to fill and collapse the bladder while we absorb the energy. Once the surge subsides, the bladder expands and forces the liquid back into the pipeline. So these are pretty good on smaller sizes. They're not very effective on a pipeline line pack because it's a bladder can only absorb so much energy. The bladder can collapse to a certain point. Once it does that, it can't do anymore. So if we absorb some of the line pack but not all of it, it's not very effective for a pipeline, unless I consider large banks of these things in parallel. And then we're getting into gets very cost prohibitive. Rupture discs. Rupture discs are another one-time use. A rupture disc is a thin diaphragm, usually a solid metal disc, which gets inserted between 2 flanges. And these rupture discs are designed to break and to rupture at a certain specific pressure. So these are a weak link element to protect our vessels. And we can see the rupture disc towards the right is showing a rupture disc as it should be. And we see what happens when the rupture disc does rupture. We've got a nice big hole in the middle for the fluid to go through. So it's a very high capacity device. It's quick to respond. But just like the rupture pin valve, once it goes, it goes. And again, in a remote area, I better get out there and close another valve in series after my surge abates before I fill up my surge relief tank. Then I've got to isolate this guy. I've got to spread a couple flanges apart, deal with the leakage or any mess that might be associated with that to replace the disc. So they're economical, but they are a one-time use. They do not modulate. And then finally, we do have modulating valves. These are 2 valves from the Daniel unit of Emerson, and we have 2 flavors of the modulating type relief valve. We have the pilot-operated valve at the top right. That's our model 761. And below that is our nitrogen gas-loaded relief valve, the model 765. Now, these are modulating. These valves are designed to open. They will relieve the excess energy from the pipeline. Once the surge abates, they will close and reset for the next, ready to go for the next time. Similar, they operate on the same basic principle, which is a balanced piston design, but the operation is different. The pilot-operated valve uses a small control pilot to sense the upstream pressure, and the main valve is a slave to the smaller control pilot. So the pilot and the valve are normally in a closed position. If we sense a surge in the piping, we'll pick that up through a piece of tubing. The tubing will cause the pilot to open, and the pilot will then tell the main valve to open. Now, the pilot-operated valve has the advantage of being completely self-contained. It's an excellent valve for low-viscosity refined products, but it has relatively slow response particularly when compared with a nitrogen-loaded relief valve. It's great for clean service, non-plugging, non-freezing. We can do some things if we're talking about dirty, nasty crude oil, but there are some limitations on a pilot-operated valve. The nitrogen-loaded relief valve does require nitrogen. This is the same balanced piston design, but this valve is unique in that this is not strictly a nitrogen-loaded valve. This uses nitrogen gas over oil, which makes the valve unique. And because we're using oil as a movable barrier between the nitrogen gas and the valve internals, we have zero consumption of nitrogen with this valve. So the valve is not affected by high viscosity fluids. It's very tolerant of foreign material in some of our nasty crude oils, and it has exceptionally fast response time. So we have, depending upon the application and what the customer is looking for, we have two approaches to this. So here's a cross-section of the 761 pilot-operated valve. On the top left illustration, we're showing the valve in the closed position. On the right, we're showing it in the control position. And the flow, our inlet pressure is the orange on the left. The outlet is on the right. On the photo on the left, we have our control pilot with a sense line going to the upstream side of the valve with a spring in that pilot. That spring is keeping the pilot in the closed position. As long as the pilot is closed, we're taking an inlet pressure from the valve and we're applying it to the backside of the piston. And because that's a stainless steel piston with equal area on both sides, if I apply the same hydraulic pressure, the piston is balanced. But you'll note there is a spring on the backside of the piston, and it is that spring bias, that spring differential, which is going to keep the valve in the closed position. The illustration on the right is showing what would happen if we did have a surge come up the line. It's going to be picked up by the sense line. That surge pressure will be enough to overcome the force of the pilot spring. The pilot will open, and that will allow the backside of the piston, the green fluid, to evacuate from the backside of the valve through the pilot to the downstream side, and that will allow the valve to open because now the inlet pressure is greater than the pressure on the backside of the valve plus the force of the spring. The valve will open, will pass the required flow rate to mitigate the surge. When the surge pressure subsides and the pressure falls below set point, the pilot will close. That will in turn close the valve, and we're ready for the next go. Showing the nitrogen-loaded valve. Again, the same principle, balanced piston design, but instead of using a pilot, a secondary pilot, this is more of a direct acting valve. We're actually supplying nitrogen gas in orange on top of clean motor oil, which is shown in gray, which sits on a reservoir mounted on top of the valve. So the nitrogen gas gets applied on top of the oil, and the oil is forcing down the piston, keeping it in the closed position. Now, that nitrogen tank, we actually call that a plenum tank. It's acting like a spring plenum. The volume of that tank is important because this is where we take into account the customer's desired maximum allowable overpressure, the typical 10%. It's important to note that this valve is not consuming any nitrogen whatsoever. What will happen here on the illustration on the left in the closed position, my inlet pressure is exerting a force on the bottom of the piston trying to open it, but the nitrogen gas is keeping it closed. On the right, we're showing a surge pressure is going to come through on the bottom side of that piston. It will overcome the force of the nitrogen and force nitrogen back into the plenum tank, allowing the valve to open, pass the required amount of flow to mitigate the surge. When the inlet pressure drops below the nitrogen pressure, the valve will close. So we're simply moving nitrogen from the valve into the tank for opening, and then from the tank back into the valve for closing. This is just a video showing the valve in operation. We see our pressure gauge on the inlet, and we've got a surge coming down the line. The instant that exceeds the force of the nitrogen, the valve comes open, forcing nitrogen back into the tank. So again, nitrogen is moving back and forth, but it is not being consumed. You'll note there's a pressure transmitter on the nitrogen tank. It is critical to monitor that nitrogen pressure because that's what's keeping the valve in the closed position. This valve is this valve responds literally in less than 100 milliseconds to a change in pressure. So it has extremely fast response. using the oil, again, we do not consume any nitrogen. This has become very much an industry standard for many of the major pipeline companies around the world. This is truly a superstar product. So, previous slide showed the most simple, basic installation of that valve possible, where we simply have the valve connected via tubing to a plenum tank, and that plenum tank was, whenever possible, buried underground or insulated to minimize ambient temperature effects and the effect that could have on my nitrogen set point. If the plenum tank is sitting out in the hot sun and it heats up, that's going to cause the nitrogen gas to expand. That will affect my set point. I want to keep my set point constant 24/7. So for those applications where it's not practical or possible to either bury or insulate the tank, or there's extreme ambient temperature swings throughout the day that could adversely affect my set point, we can supply a nitrogen panel to regulate and maintain a constant set point on that valve. This is part of the offering from the Emerson Flow Systems and Solutions Group. So, second question, how often do you functionally test or inspect your surge relief devices? You would take a moment and just give us some insight on that. Oh, that's interesting. It's no surprise that yearly is the predominant answer. I'm very pleased to see that some of these things are done quarterly. The absolute minimum from the Department of Transportation is in period not to exceed 15 months. So yearly or better, that's good. That's very good. Okay, thank you for that. All right, so now we're getting into more from this would just be the P&ID that we would show for this could be loose equipment or this could be a system. This is where we get into our modular solutions, where we can supply a simple solution as loose equipment, which is assembled and fabricated on site using these components. We've got our surge relief valve right in the middle. We have pressure transmitters on both sides of that. We also have a flow switch or flow indicator that might indicate if the valve is open. And you'll notice there's a blue line coming off the top of the valve to the nitrogen plenum, which we would hope would be insulated and or buried whenever possible. And in parallel with that, we have a line coming off going to the nitrogen panel. Now looking at the nitrogen panel, we have a high side and a low side. There's a nitrogen supply bottle rack, and these are just the simple, standard, commercially available nitrogen bottles that we use as the source. That goes into our nitrogen control panel, and through dual stage regulation, we reduce that pressure to the required set point of the valve, and that's what we send down to both the valve and to the plenum because they're in parallel. So again, the purpose of the panel is to regulate and maintain a constant set point regardless of what's happening in our plenum tank. That plenum tank, if I have huge swings in ambient temperature or if I require a very precise set point, a plenum could be advantageous to us. So this is a very simple P&ID. We always recommend that all of our pressures be sent back to our control room so we can keep an eye on this thing so we know what's happening. We want to have pressure transmitters on our nitrogen supply so that we know if our bottles are going empty. And we certainly always want to monitor the pressure at the valve because, again, it's the nitrogen pressure that's keeping that valve closed. So if for whatever reason, if we lost nitrogen, that valve could open when we don't want it to. So it's critical to monitor that nitrogen pressure. All right. Flow systems and solutions. We've taken a loose equipment and we're taking it to the next level, which is a total single point responsibility solution for surge relief. We can supply valves with plenums and panels, which can be assembled on site. We can also supply a complete surge relief system. where everything would be skid mounted, fully instrumented, nitrogen control panel, everything would be engineered, manufactured, tested, and commissioned by the Flow Systems and Solutions Group. The key features of that valve, very high capacity with a 45-degree operation. The oil barrier, again, prevents nitrogen consumption. Modular design. Once that valve is installed, it never has to come out. If there's ever a problem with that valve, I do not have to remove the complete valve from the line for service. I can simply take out the complete internals as a unit, as a cartridge, and I can replace it with another unit and minimize my downtime. On a skid-mounted system, we would supply the complete nitrogen control system. It would be designed, manufactured, and commissioned by Emerson, by the Flow Systems and Solutions Group. We supply inline testing ports. We'll do factory testing and life cycle services to ensure system integrity. Surge detection and or measurement. Many customers often want to know how much fluid has come off that pipeline. And for those customers, we can actually install a liquid ultrasonic meter along with the surge relief valve to tell you exactly how much product we did have to take from the pipeline to mitigate our surge. So this gives us optimal pipeline management, provide critical capabilities, and we've been doing this a long time. We've been building these valves for about 40 years. We know what we're doing. This helps eliminate project risk and complexity using our integrated solutions. Everything centers around the Daniel 765 nitrogen loaded relief valve. We're using the Rosemont testing class pressure transmitters. This is showing the model 3812. This is the two-path transit time liquid ultrasonic meter. The illustration on the top is showing our 8-inch surge relief system, just the valve. We've got our nitrogen panels, block valves on either side, fully instrumented. And below that, we've got the same design, a little bit longer, because we've inserted a 3812 two-path liquid ultrasonic meter right where the arrow is. So this will allow us to not only eliminate the surge, but also to measure just how much fluid that we have to take off the pipeline to do that. So, surge relief protection, we need it for production, we need it for transportation, anywhere there's storage. Again, it's not just pipelines, terminals, refining, FPSOs, transportation distribution pipelines, tank farms, pump stations. We talked about some of the surge sources. Marine operations, very common use of this device. For loading or offloading, this is showing an unloading operation where we're unloading a ship to an onshore terminal going through a metering station. We have our emergency shutdown device on the far left going into that onshore terminal. In the event there is an emergency and we do have to shut down the emergency shutdown device, we have our surge relief valve coming off the branch, and that will remove that excess energy into our relief tank, thereby protecting everything on the jetty and or the ship. FPSOs, another very common application for surge relief, where we're dealing with pump failures, blackouts, emergency shutdown. There could be emergency release coupler. All of these require very fast-acting valves because you got to shut things down in a hurry. So we've got to have extremely fast-acting valves to minimize and mitigate those surges. So just to wrap up here, again, it's not just pipelines. It's anywhere we have liquid flow, we do have the potential for surge. So we need to be aware of it. We need to be constantly thinking about it and take the steps that are necessary. This is a partial users list of some of the users of the Daniel Surge Relief solutions throughout the years. And we also have some additional resources here. You can go to our website, www.daniel.com. We have a Surge Relief Systems homepage, and from there we have a technical guide, which is a great primer about surge relief. It talks about the sizing of the tank, the sizing of the valves. We have a systems brochure and a product data sheet. That's all available to you. I think those links will be supplied. And at this point, I'm going to turn it over to Allison because hopefully we got some questions that come in. Allison?
We do, Dave. Thank you so much. Thank you so much for all this great information. As Dave just mentioned, I want to point out all those resources on the previous slide are also available in the resource list on your webinar console here, and you can download them right from here for easy access. As Dave mentioned, we're now going to open it up for questions, so please use that Q&A chat panel. Dave, we do actually already have quite a few questions in the queue, so I'll let you get to it because we've got about 13 minutes.
Okay, thank you. All right. Does a nitrogen-loaded valve respond faster than a pilot-operated valve? Yes, it does. Simply from the fact that, well, there's a couple things going on here. One, the pilot is actually a much smaller control valve, and it has limited capacity. And when we start talking about 8, 10, and 12-inch mainline valves, there's a fair amount of fluid that has to be evacuated from the backside of the piston that's got to pass through the pilot in order to allow the main valve to open. The nitrogen-loaded valve does not use a pilot, and for that reason alone, many customers in the critical applications of relief prefer the nitrogen-loaded valve over a pilot-operated valve for the simple reason that the nitrogen-loaded valve is more of a direct-acting valve. With the pilot-operated valve, two things have to happen in order to eliminate the surge. The pilot has to respond, and then the main valve has to respond. Well, if the pilot doesn't work, then the main valve's not going to work. So the main valve is a slave to the pilot. By eliminating the pilot, we're eliminating 50% of the things that can go wrong. So the nitrogen-loaded valve is much faster in response than a pilot-operated valve. All right. What modeling software is typically being used? In the past, we have not done any of the analysis. In fact, we're still not doing any of the analysis ourselves, but we are working very closely with ESI and their Pipeline Studio suite to incorporate the characteristics of the Daniel valve so that they can better provide modeling for their users. So today, we're in the early days of getting more closely aligned with Energy Solutions International. So very good question. Thank you. Oh, this is a good one. What's the pipeline length, pressure class, velocity, valve closing times where surge should be analyzed, considered? I've not seen surge in the pipelines I've worked on, which have been class 150, less than 10 feet per second and less than 3,000 feet long. Well, to the first part of the question, I don't think there's any pat answer to that. I don't think we can say less than 1,000 feet, consider above 1,000, or less than 1,000 feet, you don't have to consider above 1,000 feet, you do. A lot of that has to do with velocity going through there. Now, 10 feet per second is a fairly low velocity for a pipeline, but 3,000 foot is a fairly short distance also. I've seen some bulk loading terminals flowing at some smaller sizes, but at some pretty high velocities. And at the loading terminal itself, when the valves loading tanker trucks are slamming open and slamming shut, pipe racks shake, and it gets a little bit scary up there. So I don't know that there's a pat answer to what is the length, class, velocity, closing time where surge should be analyzed, considered. I would encourage customers to take advantage of some of the modeling software that is available, and that's really where you're going to figure out if you need it or not. Not seeing surge in the pipelines, which have been class 150, less than 10 feet per second and less than 3,000 foot long. Well, a lot of that could have to do with the valves that you got. If the valves are slow closing and there's not a lot going on up there, I could certainly see where you would not develop surges. But I would think on a 10 foot per second, 3,000 foot pipeline, if we slammed a valve shut at the end of that thing, I don't think I'd want to be close. I think we'd be dealing with some fairly significant surges. Please talk more about the surge tank downstream of the surge relief valve. Does the tank need to be rated to a MAWP higher than pipeline? How do you determine surge tank capacity? That's a really good question. Normally, these tanks are vented to atmosphere because we're talking about, for the most case, refined products and crude oil. So we don't expect the tanks to see much pressure at all. They need to be vented, actually, and they need to be vented to the point that whatever's coming in can be vented out without building up pressure. How do we determine surge tank capacity? That's a great question. In the case of a modulating valve, we expect the valve to close after the surge abates. So once we do our computer modeling and we determine how quickly we need that relief valve to open, what type of flow rate do we need to remove the excess energy from the pipeline, and how long do we need to flow before the surge subsides, that will give us an idea of the total volume we would expect to evacuate from the pipeline in order to mitigate the surge. And then I would want to put on one quite large safety margin on top of that. So it's a great question. It's one that we often have with some of the customers. But again, the sizing will help answer some of those questions. The modeling will tell us how quickly the valve needs to open, what the flow rate needs to be to mitigate the surge, and how long do we need to flow before that surge pressure abates and the pressure comes back to normal. Knowing rate and knowing time, we can calculate the volume, and from there we can figure out what size tank we need with an appropriate safety margin. Are sour crude compatible versions of the serve relief valve available? Yes, we do have NACE trim on our valves. Crude oil, we're seeing more and more applications for crude, so we have developed and released NACE trim on most sizes. What's the advantage of using nitrogen instead of using a spring like a regular relief valve? With that, we don't have to deal with nitrogen and control to keep it under pressure setting. Excellent point. You're absolutely right. One of the advantages of a spring-loaded direct-acting relief valve is you don't have to apply anything else with it. But we have to talk about, depending upon your capacity, what kind of flow rates are we looking for? We're not going through a reduced nozzle. We've got some very high C sub V's capacities for our relief valve. We have infinitely variable settings on our valve. I can take within, well, let's put it this way. The set point of any of our relief valves are anything from 10 up to the maximum working pressure of that valve. So, for example, an ANSI class 150, I can have a set point anywhere from 10 to 250 psi through one valve because I'm simply adjusting my nitrogen pressure. The bigger advantage that the nitrogen-loaded relief valve has is a constant set point. As I mentioned earlier, the spring-loaded device, when you lift that seat, when you lift the plunger off the seat and compress the spring, that spring force is increasing dramatically. So a valve that might pop off at 200, when that thing comes off the seat just a little bit, now your spring force has gone from 200 to possibly 230 or 250 psi. So if your incoming pressure is at 230, let's say the valve pops off at 200, we start flowing through there, but then we've compressed the spring to 250, that valve's going to slam shut again. So now we're sitting here with the valve chattering close to its seat. So those are some of the issues and some of the concerns that customers have reported to us about using the spring-loaded device. How accurate is the ultrasonic meter in the highly dynamic transient flow conditions that occur during surge relief? Great question. Initially, we've had some customers had a preference to install the flow meter on the outlet of the relief valve, and we said, no, that's not a good idea for a couple of reasons. One, often the outlet of the relief valve is open to atmosphere or to an empty pipe. So we don't want a liquid ultrasonic meter sitting there with an empty pipe. It will just give us nothing but false because the transit time signal from the transducers, they're designed to go through liquid. They won't pass through air. And then the second issue is because it's a control valve that's modulating, we're going to have severely different flow profiles going into the ultrasonic meter if we have the meter installed downstream from the valve. But by installing the meter upstream from the valve with minimal flow conditioning and full port valves upstream from that, we've got relatively good enough flow conditioning that we'll get reasonably good results. Now, the ultrasonic meter is not there for custody transfer. It's a two-path meter to begin with. So we want something that is obstructionless. We don't want to put a turbine meter in there or something that's going to have rotating parts that could come flying out and damage our valve. So we want a straight-through design meter, which the ultrasonic meter is. We want reasonably good accuracy, and we've got sufficient straight pipe upstream to ensure that we do get that, at least to within the linearity of the meter, which is plus or minus 0.3%. But again, this is not considered a custody transfer meter. This is just to give us an idea how much fluid has come off that pipeline during a surge event. Please review the difference between packing pressure and surge pressure. Briefly stated, surge pressure would be if we, again, I'll use the analogy of a bathroom tap or a kitchen tap in an older house where we've lost the air cushion. If I open my tap fully and then close it very quickly, sometimes I can hear some rattling going on in the pipes. That's the water hammer or surge. That's an instantaneous conversion of momentum to pressure. Packing is somewhat different in that packing occurs on the end of a long length of pipeline. In my house, when I stop the flow of water, I've stopped pretty much the flow of water everywhere. So I just get that instantaneous shake. That's my surge. Water hammer on a long column of liquid, if you can imagine a long pipeline, could be, again, hundreds of miles long. And if I stop one end of that pipeline, guess what? The other end of the pipeline doesn't stop. And inertia, momentum, there's a huge column of liquid, tremendous energy there. That momentum carries on through, and that pressure will gradually build up at the other end of the pipe where that blockage is. That's line pack. That's why that's such a serious concern for the pipeline operators. Great question. If a nitrogen panel is utilized, how often do the nitrogen bottles have to be replaced? That is dependent on how tight is the set point, because we have plus or minus tolerance on the valve set point. So the tighter the set point, the more nitrogen that we're either going to evacuate to atmosphere in case the pressure gets a little bit too high, or more nitrogen that we'll have to put back onto the system to bring it up to the required set point. So it's the set point tolerance. How much is the temperature affecting the bottle? How well can I insulate my plenum tank? The better I can insulate my tank, the less nitrogen consumption I'm going to have. In fact, if I can insulate that panel and the valve to the point where ambient conditions have almost no effect on my set point, I will have almost no nitrogen consumption. Many of our customers, I showed you in our diagram, we simply had the valve and a piece of tubing going to the tank, and that tank has been buried underground. We've got some major pipeline companies here in the Houston area that is the system they've elected to use. They literally put their plenum tanks and they bury them underground. They have a pressure transmitter. We always recommend the pressure transmitter. But they bury the tank underground and they run a line from the tank to the valve, and that's it. There is no panel. There are no bottles. What this requires is an absolutely perfectly bubble-tight installation. We cannot have any leaks around any of the fittings, around any of the isolation valves, around any of the transmitter, any of the threaded unions. We've got to use top quality hookup. But if we can do that, if we can ensure a leak-free installation, it is possible to install our valve with a line going to a plenum tank and nothing else. Now that's because we're using nitrogen. If I did not use nitrogen, I could not do that. And the reason I could not do that, if I apply nitrogen directly on the backside of my piston, nitrogen can and will permeate the seals around that piston and pass through to the other side. So I will have, in effect, a very, very slow leak of nitrogen from my plenum tank into my process fluid. Well, a little bit of nitrogen getting into crude oil is not going to be a problem. But if I eventually lose my pressure in my plenum tank, that's going to be a huge problem. Because we use oil as the nitrogen as the barrier between the nitrogen and the valve, we don't have that problem. Great question.
All right, Dave, I'm going to jump in there because we're at the top of our hour, and we thank everybody for the numerous questions. We have a very large backlog, which will keep Dave busy, but he will email you the answers. So we really appreciate everyone's engagement. I even see more questions coming in right now. So we thank you very much. Just to remind everybody, if you do have any additional questions even after this, you can submit them through this environment. You can email Dave, and we'll get back to you. We will also be sending out a link to the recording tomorrow, so you can listen to this again or share it with your colleagues. We want to thank you again for joining us today and for all these great questions. Again, Dave will be emailing everybody that we missed the questions to because we do have a large backlog. On behalf of our guest, Dave Seiler, as well as everyone here at Emerson, we again thank you for joining us on this webinar, taking the time to view the presentation, and engaging with us with all these great questions. Have a terrific day. Thank you.
Thanks, everybody.